X-rays and CT scans measure physical density. Bone blocks radiation, air lets it pass. But with magnetic resonance imaging, that physical model stops entirely. An MRI doesn't measure how effectively a tissue blocks a beam. Instead, it measures how hydrogen protons behave after being disturbed by a magnetic pulse, tracking their precise rates of magnetic relaxation. This equation illustrates the baseline reality of the human body. Inside the scanner, every tissue simultaneously exhibits three inherent magnetic properties: its total proton density, its T1 recovery time, and its T2 decay time. Because tissues exhibit all three properties at once, turning on the machine and simply recording the immediate response results in mutual interference. The signals overlap, yielding a low-contrast wash of gray, where healthy tissue and pathology are indistinguishable. Achieving diagnostic contrast requires temporal isolation. We have to systematically filter out two of these variables to clearly see the third. The radiologist controls this isolation using two specific timing parameters on the scanner console: TR, the time to repetition, and TE, the time to echo. TR dictates the millisecond interval governing how often the machine fires its 90-degree radiofrequency pulses. TE dictates the specific time delay before the scanner actually listens to capture the resulting magnetic echo. By mathematically pairing specific lengths of TR and TE, we can isolate T1, T2, or proton density, while completely neutralizing the other two effects. We can map these parameters onto a standard 2x2 matrix. We have TR on the y-axis, divided into short and long intervals, and TE on the x-axis, also divided into short and long. Mastering the exact mechanics of this grid allows you to predict sequence weighting under any condition, making it a critical framework for clinical practice and for passing the FRCR exam. Let's isolate T1. Mathematically, T1 is the time it takes for the longitudinal magnetization vector, or MZ, to recover after a pulse. Different biological molecules recover at different speeds. Fat recovers quickly, meaning it has a short T1. Water recovers slowly, meaning it has a long T1. Looking at the upper left quadrant of our matrix, to capture the maximum difference between these tissues, we fire the next RF pulse exactly when their vectors are furthest apart. Catching this point requires a short TR, between 300 and 600 milliseconds. But maximizing T1 is only half the equation. To shield our isolated signal from T2 decay, we select a short TE, usually 10 to 30 milliseconds, forcing the scanner to read the signal immediately before significant decay occurs. The resulting image is heavily T1 weighted. Fat appears bright because its signal fully recovered, while water appears dark because its recovery is still lagging. The logic holds. A short TR actively forces the T1 contrast, while a short TE acts as a shield to protect it from T2 decay. Now we shift focus to T2. This is the decay of the transverse magnetization vector, or MXY, returning to zero after the pulse. The biological baseline here is inverted. Fat loses its transverse signal rapidly, giving it a short T2. Water retains its signal much longer. Moving to the lower right quadrant, to maximize T2 contrast, we have to wait. We let the fat signal die out, leaving the persistent water signal. Capturing this delayed difference strictly requires a long TE, spanning 90 to 140 milliseconds. We have our T2 contrast, but must prevent T1 recovery differences from altering it. We select a long TR, over 2000 milliseconds. This gives all tissues enough time to fully recover to 100%, effectively erasing all T1 contrast. In this T2 weighted image, water appears bright because it retained its signal, and fat appears dark. A long TE generates the necessary decay contrast, and a long TR acts as a biological reset button to neutralize T1. This leaves an interesting physics problem. How do we configure the machine to ignore magnetic relaxation times entirely and strictly count the raw density of hydrogen nuclei in a voxel? The radiologist must intentionally crush both T1 and T2 contrast at the same time. Looking to the lower left quadrant, T1 is neutralized by allowing full longitudinal recovery, so we dial in a long TR. T2 is neutralized by reading the echo immediately before decay begins, pairing that with a short TE. With the timing effects removed, the returning signal strength is dictated entirely by the sheer volume of available protons. The outcome is proton density weighting. Both fat and water appear relatively bright simply because they are highly concentrated with hydrogen. Proton density weighting proves the mechanics of the temporal filter. The radiologist achieves contrast by systematically muting all temporal magnetic effects. We have one final empty quadrant in the matrix, the combination of a short TR and a long TE. In the upper right quadrant, the sequence fails. Short TR interrupts recovery, generating a weak initial longitudinal vector. Then the long TE forces a long delay. The transverse signal decays to 0 before the machine listens. The sequence is starved of signal, rendering it clinically useless. This dead zone proves that TR and TE are not independent toggles. They are a multiplier matrix. Poor timing choices compound and can completely annihilate the diagnostic image. Moving from conceptual graphs to rigid application, we can consolidate this entire matrix into a single reference tool. This table summarizes the strict rules mapping TR and TE timings directly to the resulting brightness of fat and water. T1 relies on short parameters. T2 relies on long parameters. PD mixes a long TR with a short TE. MRI contrast is an engineered process of temporal filtering. The scanner never actually sees anatomy. It computes vector magnitudes at highly specific millisecond intervals. By mastering the strict parameters of the TR and TE matrix, the radiologist translates that raw, invisible quantum mechanics into a precise diagnostic tool. You control the timing, and the timing controls the image.